So this video is on second order kinetics, integrated rate laws. Now, a second order rate law is something where if you, and difference rate law looks obviously like that. If you double the concentration of A, the rate will quadruple. If you triple it, it'll go 9 times faster. If you do it 4 times greater, it goes 16 times faster. You should be able to look at data and maybe recognize this if the numbers are easy to work with. So let's make sure this is not zeroth or first order by just looking at the data. Now, if it was zeroth order, what we would expect would be that if we look at a consistent time interval, the change in concentration would be consistent as well, because the graph of concentration versus time for zeroth order is a straight line with a negative slope. So what I chose are to look at the concentration versus time and to look at the interval of 1800 seconds and to see if the change in concentration for this reactant was the same for the first two 1800 second intervals. And what I found is in the first 1800 second interval, which is from here to here, and I subtracted these two numbers over here, I got 0.00524. In the second 1800 second interval, from 1800 to 3600, when I subtracted 0.00476 from 0.00313, absolute valuing it, the difference basically, I got 0.00163. These values do not match, which means the concentration versus time graph would not give me a straight line. It's not zeroth order. I can then look at the next data table and figure out whether it's first order. So I can look at the plot of the natural log of the concentration versus time and look at regular intervals and see if I get a regular change in natural log. Because again, if it's first order, then the natural log of concentration of time should give me a straight line with a negative slope. Right, so the values are going to get larger and larger negative numbers, but if I go for the same 1800 seconds, I should get the same difference between those numbers. And I don't get that. When I go from 0 to 1800 seconds, the first interval is 0.743. When I go from 1800 to 36, the next one is 0.419. I don't have another 1800 exact second interval, but I got 5200, which is getting close. And that change is only 0.261. So the natural log of the concentration versus time would not give me a straight line. Okay, you would have a changing slope. It's not first order. If I then look at 1 over the concentration, right? And when you integrate this equation number 3, you get something that has 1 over concentrations. Again, I do not remember calculus or how to do integration, so kudos to you that do. We're not doing that, all right? If you look at the same time interval, though, I can see, okay, that the change is the same during the same time interval. So for the first 1800 seconds, 1 over the concentration gives me a change of 110. For the next 1800 seconds, from 1800 to 3600, it goes from 210 to 320. It changes by another 110. And when I go from 3600 to 5200, I get a little bit less than 110, right? I get like 95. But, if I had another 200 seconds, it probably would get up to 110, wouldn't it? So 1 over the concentration versus time should give me a straight line graph. The difference is in this case, as the numbers you can see, they're getting larger, so the slope is going to be a positive value. So when if you graph 1 over the concentration like you have here versus time, and you get a straight line with a positive slope, it is second order. A couple of things to note about this graph. The y-intercept is 1 over a0, right? Right, this is 1 over a0 right here, okay? The slope, okay, is going to be equal to the rate constant, not negative. You don't have to negate this time because it's already a positive value. So the slope, okay, of this line is equal to the rate constant, which leads us to 2 different formulas, which I'm going to talk about, and 2 different types of problems. And again, I don't think you're ever going to have to, you never have to integrate, but you should maybe know these 2 formulas, okay? So the first formula is another equation that looks like a straight line, in which y is 1 over a at time t, the y-intercept, or the b, is 1 over the original concentration, and then you have k, which is the slope, and t, which is your x value, right? So you get y equals mx plus b again, where m is k. I should put mx, but I just couldn't help myself. M is k, and x is t, and b is 1 over the original concentration, and y is 1 over the concentration at time t. The other formula you're going to have here is this one over here. And the reason why I'm putting this up here is because this one involves some algebraic manipulation, and they give it to you on the AP reference tables because they don't expect you to do that algebra manipulation. Now, what you want to notice is the half-life in this particular case, unlike first-order kinetics, is dependent upon concentration. Now, two different things I want to do here. I want to talk about how you get the rate constant for second order and how you get the half-life, okay? How you get the rate constant is by using this con right here and doing delta y over delta x, because that's the slope, and you don't have to negate it because it's going to be a positive slope. So what I did was I took the final 1 over the final concentration, which is 481, and 1 over the original concentration, 100, and I subtracted and found the difference, right? I put that over the total time that passed, which is 6,200 seconds. When I do that math, I'm going to break out, I have this calculated somewhere, I have to find it. I get it comes out to 381 over 6,200. Notice you're going to have molarity ms to the minus 1, which is the normal rate constant you would expect for something that's second order, right? And so when you do this, you get you end up with you can check it with your calculator, you really should. You get 381 over 6,200, and then you get 0.00614, and the units are molarity s to the minus 1. And that's the rate constant. And you can then use that to figure out the half-life. Now, the half-life, what's critical for you to recognize is, in order to get the half-life for this guy, you're going to have to use the original concentration here, okay? So essentially, you can plug these numbers in here. So I'm going to plug the numbers in. And so what I did was I put the 0.00614 on the bottom, the original concentration, right, which is 0.01, and the one on the top, and I solve for T1/2, and I get, 1 point. And by the way, the units will end up being seconds because the molarities will, cancel each other out because of the units of the rate constant, and because the concentration is a molarity, the m cancels each other out, and you end up at 1.63 times 10 to the third seconds. These calculations are not difficult as long as you understand what you're seeing here. Second order kinetics, okay, a straight line with a positive slope when you take the time versus 1 over the concentration on your y-axis. The slope, the delta y or the delta x for this graph gives you the straight up rate constant. The units are going to be molarity per unit of time, okay, and for half-life, you're going to have to actually use the original concentration. Note, if you had a different concentration here, okay, the half-life would be different. All right, you would have a smaller number on the bottom, so you end up with a bigger half-life, basically. Okay, thank you, and have a wonderful day.